So good morning, everyone. So good evening, everyone. We will be starting in five minutes. Okay. So good evening, everyone. So it is 6 o'clock exactly. So we will wait for 5 to 10 minutes for other people to join in as well, and then after that we'll start. So let us start. So I welcome every one of you to this lecture of problem solving session on for the course of NPTEL course of thermodynamics of fluid phase equilibria. So myself, Bharat, so I am a PhD student and a PMRF fellow at the Department of Chemical Engineering at IIT Kanpur. And let us begin with the week 2 problem solving session. So I will be going with the first question. Yes, yes. So the first question is as follows. Keeping in the limitations imposed by the second law. Yeah. So keeping in the limitations imposed by the second law of thermodynamics, choose the wrong statement. So in case you have forgotten, so we have the 4 laws of thermodynamics. The first 3 laws, the zeroth law, first law and second law, these were covered in the previous week, whereas the third law is covered mostly in this week. The third law is law of entropy, which basically determines the entropy, which says that there are various interpretations of the third law. So one of the interpretation is that the entropy of the perfectly crystalline substance, that is entropy at absolute zero temperature is zero. So basically, zeroth law tells us that there is a quantity called as temperature. First law basically tells us that heat and work are forms of energy and they are interconvertible. However, first law does not give us the uh, how much amount of it can be converted into work and vice versa. Second law gives us the tells us that all the heat cannot be converted into work, whereas all the work can be converted into heat. And the third law, like I said, absolute zero is zero. Okay. Question. So the question is, so the question is, keeping the limitations imposed by second law of thermodynamics in mind, choose the wrong statement below. So a heat engine cannot have a thermal efficiency of 100%. Okay, this is the first option. For all the reversible process, the second law efficiency is 100%. The second law efficiency of heat engine cannot be greater than its thermal efficiency. And the second law efficiency of a process is 100% if no entropy generation, if no entropy generated during the process. So clearly, like I said, all the heat cannot be converted into work. So we cannot have a thermal a heat engine which can have 100% efficiency. So option A seems to be possible answer. So let us go to option B. So for all reversible process, second law efficiency is 100%. This is wrong. Okay, so the option is second law efficiency of a heat engine cannot be greater than its thermal efficiency. This is also a wrong statement. The final option is the second law efficiency of a process is 100% if no entropy. So no entropy generated, that means it's a reversible process. So even in reversible process, we cannot have 100% conversion of heat into work. So clearly the correct answer is option A, right? Option A is the correct answer. Heat engine cannot have a thermal efficiency of 100, greater than or equal to 100%. Okay, so anybody has any questions? So I'll wait for 1 minute. If anybody, so the correct answer is option A. Okay. So if nobody has any questions, we'll move. Okay. So we will move. So like I said, the second law of efficiency of heat engine cannot be greater than its thermal efficiency. Okay. That's why option is C. Option C. Okay. So we'll move on to the next question. Okay. So which of the following statement of so which of the following statement of so the second question is which of the following second law statement is incorrect. Okay, so it's a tricky question. Here they are asking which is wrong. Okay, which is, they are not asking the second correct interpretation of second law, but they are asking the incorrect interpretation of second law. So the entropy of isolated, so the option A is entropy of an isolated system must remain constant or increase. Okay. Entropy of a hot copper block decreases when it cools. Okay. If ice is melted in the water in an insulated container, the net entropy decreases. The work must be input if energy is transformed from a cold body to a hot body. Okay. So which of the following is incorrect? Okay. So if anybody wants to answer, they can try. Entropy of a hot. Okay. So let us start. So this clearly is a correct statement. Entropy of a hot copper block decreases at its cools. So as the temperature decreases, we go from more random state to less random state, and entropy is nothing but the directly related with the randomness. So entropy of a hot as the temperature decreases, the entropy decreases. So this is the correct answer. If ice is melted in an insulated container, the net entropy decreases, right? If the ice is melted in water in an insulated container, the net entropy decreases, right? So anybody would like to answer? Okay, so this is a the net entropy when this is said, it's a net entropy of the system. Okay, entropy of the system decreases. So this is a correct. Remember that entropy of system plus surrounding should increase or it should remain constant, whereas entropy of the system individually can increase or decrease. Okay, so work must be input if energy is transferred from cold body to a hot body, right? So this is also correct. Okay, because we know that heat can only transfer from a body at a high temperature to a lower temperature. Okay, so our correct answer is option A. Okay, so anybody has any questions? If no, then we will move on to the next question. Okay, so the next question is question number 3. Okay, so what is the question? Let us look at the question. The absolute entropy is 0 for all crystalline substances at 0 temperature. So this statement is known as, really it's the second law of thermodynamics, third law of thermodynamics, right? It's the third law of thermodynamics. So let us revisit. So what does the zeroth law of thermodynamics tells? Zeroth law of thermodynamics tells that if body A is in equilibrium with body B and body B is in equilibrium with body C, then body A and body C are in equilibrium. Okay, so basically it tells that as these two systems are in equilibrium, there has to be a quantity which has to be same for both this system, and this establishes quantity called as temperature, which has to be same. Okay, temperature. So it gives us the zeroth law gives us the definition of temperature. The first law tells us that heat and work are interconvertible. Okay, heat and work are interconvertible. Okay, delta U is equals to delta Q plus minus delta W. Okay, so this depends on the sign convention which we are using. So heat and work are interconvertible. However, first law does not give us that how much amount of heat is converted into work and how much amount of work is converted into it. That is given by the second law, which tells us that conversion of heat into work 100% is not possible. However, conversion of 100% work into heat is possible. Okay, and the third law basically tells us what? So what does the third law tells us? Third law tells us that entropy at absolute zero temperature is zero. That means entropy of the permanent crystalline temperature at absolute zero temperature is zero. So this is this one. Okay, so the correct answer is option C. Sorry, option D. Third law of thermodynamics. Okay. Anybody has any questions? I'll wait for 1 minute. If anybody has any questions, they can ask.
No, sir, no question.
Okay, okay. So we'll move on to the next question. Okay. So the next question is, the volume expansivity beta is defined as this: 1 by V, dou V by dou T at constant pressure. Okay. So we have to find, so where V is the volume of the gas, T is the temperature, and P is the pressure. So what we have to do, we have to find this volume expansibility for an ideal gas. Okay. So how will we calculate? So first, write what is the expression for ideal gas, equation of state. So what we have is PV is equals to nRT. Okay. So you give V is equals to nRT by P. Okay. So from here we can say V is a function of T and P, right? Because N and R will be constant. Or you can say for an open system, NTP. For a closed system, V will be a function of T and P only. Okay. So we are considering here closed system. So here when we say, so we are saying is a closed system. Okay. The number of moles are also not varying. So it has to P and N. Okay. So what we have, V is equals to nRT by P. Okay. And V is a V of T and P. Okay. So let me erase this and then we will go. Okay. So let me just rewrite it. So what we have is, this is P and N closed system, and P is equals to N R T by V. Or we can say that V is equals to nRT by P, and V is equals to V of TP. Okay. So as the volume is a thermodynamic property, what we can do, we can write it as V is equals to, or dV is equals to dou V dou T at constant pressure dt plus dou V dou P at constant T dP, right? And if we divide this by temperature or volume, what we get is 1 by V, here 1 by V, here 1 by V, and this whole thing. Okay. You can see this is related to this. Okay. So we can say that this is beta. So what we can say is dV by V is equals to beta dt, and this quantity here, this quantity, this is called as isothermal compressibility, negative of isothermal compressibility. Okay. So then hence we can write minus K dP. So this is just a information per se. Okay. Now for an ideal gas we have to find. Okay. So for ideal gas we have this. So what we can do is, we can just rearrange it and we can write PV is equals to nRT. Okay. And then we can take a partial differentiation. So P dou V dou T at pressure, constant pressure, will be equals to dou by dou T of, so I've taken P, so we are basically taking derivative of LHS and RHS with respect to temperature, and pressure. Pressure comes out of the derivative because it's constant. Okay, and this is nRT. Okay, so now P into dou V dou T P is equals to nR into dou T by dou T. Okay. Why? Because N and R are constant. So that means we can write P is equals to P into dou V dou T. P is equals to NR. So now what we want is, we want this, but we want to divide it by V. Okay, so we divide it by V, we divide it by V, and we rearrange. So P comes here. So basically what we get is 1 by V into dou V dou T. P is equals to NR by PV. Okay, but we can again use this expression here, right? We club it here. So from there what we get is NR by PV is nothing but 1 by T. This implies 1 by V dou V dou T. P, okay, dou V dou T P is equals to 1 by T. Okay, so for ideal gas, and this is nothing but beta. So beta is equals to, for ideal gas, is 1 by T. So option B is correct. Okay, right? So you can see here as well. So let me first remove it. Okay. Okay. Anybody has any questions? Otherwise, we'll move forward. So you can see it here. Okay. Isothermal compressibility, beta is equal to this. For ideal gas, we have for we just take PV is equals to nRT for ideal gas, and we do the differentiate. We replace V, it will be nRT by P. Okay, and then as pressure is constant, P comes out, and then RR also constant, it also comes out. So what we get is 1 by V already out from here, and R by P comes out, and it comes dou T by dou T, which comes out to be 1. Okay, so this multiplied by 1, and then we again resubstitute this NR by PV, so it comes out to be 1 by T. So answer is option D. Okay, so if anybody has any doubt, they can ask. Otherwise, we'll move on to the next question. Okay. You can see the next question as well. So in the next question, what we are asked is the, isothermal compressibility has been given. Okay, isothermal compressibility, definition of that. Okay, for an ideal gas, we have to find what is the value of kappa. Okay, so this is called as K kappa, and it is full form is isothermal compressibility. Okay, so we will do the similar process. So we will go here. So we have PV is equals to nRT. Okay, then we take the derivative of this expression, both LHS and RHS, with respect to pressure at constant temperature. Okay, so what we get is dou by dou T of PV is equals to dou by dou T of nRT. Okay, but this has constant temperature, right? Because here constant temperature and constant N. Okay, because it's a closed system. So Tn, so we will Tn. So now onwards we will not write N, we will assume it, okay, that it is constant. So this comes out to be constant because n is also constant, r is also constant, and t is also constant. So this comes out to be derivative of a constant. Let's say we say c. So this is nothing but 0, right? So then we have, and we then do this. So what we get is dou p dou t. So basically how it comes is, okay, so p into, so we apply the product rule, dou v dou t, okay, dou p, okay, so we are taking with respect to p, okay, so here it's not t, it's p, I think. Okay, let us redo it. Okay, so let us go down and let us go here. Okay, so what we have is isothermal compressibility K, and its expression is gas minus 1 by V dou V dou PT. Okay, so for ideal gas, we just replace, we have PV is equals to nRT. Okay, so we just replace, okay, so we just replace it, and then we get PV is equals to nRT. Okay, then we replace the V is equals to nRT by P. We substitute this in this, and then we get this expression. Now temperature is constant, so it will come out. Okay, and when you simplify this expression, so 1 by V remains 1 by V minus 1 by V, and this expression comes out to be minus nRT by P square, and which is within you again. So how can you write 1 by V into minus nRT by P into P? Okay, 1 by P. Okay, 1 by P. So this cancels out with this, and we get 1 by P as an answer. Okay, so 1 by P. So correct answer is option D. Okay, so anybody has any questions? I'll give 1 minute. So these two are the for ideal gas, this isothermal compressibility and beta volume expansivity. For ideal gas, these are the very common questions which can be asked and which you should know by heart. Okay, so we'll wait for 2 minutes and then we'll go to the next question, which is also quite confusing question. Okay, so nobody has any questions. I'll give 1 minute. So by that time, let me erase this. Okay, then let us read the next question. So we'll go on to the next question. Okay, so what is given in the question? For liquid acetone at temperature 20 degrees centigrade and 1 bar, the volume expansivity P. Okay, so it's possible that the all the time the expression for beta and isothermal compressibility K is not given. So you have to remember it. What is beta? So beta is equals to 1 by V dou V dou Tp, and K is this one. Okay, so this expression you have to know. Okay, as this is not given in this question. Okay, so we will continue reading. So what we have is for a liquid acetone at 20 degree centigrade and 1 bar. So we are given initial temperature, let's say Ti or T1. This is 20 degree centigrade, and P1, which is 1 bar. Okay, and the volume expansibility beta is given as this 1.49 into 10 to the power minus 3 degree centigrade inverse, and the isothermal compressibility K is given as 62 into 10 to the power minus 6 bar inverse. Okay, so beta is given as 1.49 into 10 raised to power minus 3 degree centigrade inverse, and kappa is also given. The isothermal compressibility, which is 62 into 10 raised to power minus 6 bar inverse. Okay. And what are we asked to find? We are asked to find if beta and k. So remember, beta and k are constant. This is the condition which they are imposing, and then they are asking us to find dou t, dou p by dou v, dou tv. Okay. So remember that we cannot use this expression. We can use this expression, but we cannot use this expression. Okay. Here, which we discussed in the earlier questions, earlier two questions, because those equations are valid only for ideal gas. Okay. And here, then nothing has been mentioned of ideal gas. It is a liquid acetate. Okay. So real liquid mixture we are talking. However, the definition, this definition we can use. Okay. So let us. So if anybody would like to try, I'll give you 2 minutes to try. Okay. I hope the question is clear to everyone. Okay. Anybody has any questions in the understanding the question? If no, then I'll give you 2 minutes to try it out. Okay, anybody would like to answer? Anybody got the question? So let me try with the beginning. So I'm repeating it again, but I think a certain level of repetition is good so that you will be able to grasp it. Okay. So again, what we as a, so how do you hear the formula for this is not given. Isothermal compressibility and volume expansivity is not given. So we are going to first derive. So so if I derive it multiple times, you will be able to remember it. Okay. So V as a function of TNP. So we just write this thing, dV. This is we are using the definition of thermodynamic property. So we are expressing volume as a function of temperature and pressure. So dV will be what? Partial derivative of V with respect to T at constant pressure dt plus dou V dou P at constant temperature dP. And then we are going to divide this by V. So here we will be getting 1 by V. Here we will be getting 1 by V. And this expression, we are calling it as beta. And this expression, we are going to call that minus K. So what we have is dV by V is equals to beta dt minus K into dP. Okay, where beta is equals to this and minus negative kappa is this. Okay, so with this established, we'll go to the next part of the solution. Okay. Okay. So here I am again repeating it. Okay. So I already tell B as a T and P. So we can write it as this expression and then we divide it. So we get this expression. And here in the question it is mentioned that volume is constant. Okay. So where is it mentioned? Volume expansivity. Okay. So here explicitly it's not mentioned, right? The volume it's given beta and K are constant. Okay. But you can see that it's a liquid acetate, right? That means its volume is more or less going to be the same. Okay. That is why we say dV is equal to change in volume is 0. So this is 0, 0 by V, which is nothing but 0. So we have 0. So we replace this by 0. So 0 is equals to beta T by KdP. And then we rearrange it. So the one step between this is so just if you look at this, so then we can rearrange it is beta dt is equals to kappa dp. Okay. And then you rearrange it So then we get it what? So then we get it is you just tt you take this side and k you take this side. So we have dou p by dou t at constant value. Remember this is constant value because we are assuming that we are dv is 0. Okay, dv is 0. This is equals to, you rearrange it, beta by k, and for us what is that beta? Beta has been given as, okay, beta is given, okay, beta is given as 1.49 10 to the power minus 3 degree centigrade inverse, and kappa is 62 10 to the power minus 6 bar inverse. Okay, so then this is beta is 1.49 10 raised to power minus 3 degree centigrade inverse divided by 62 10 raised to power minus 6 bar inverse. Okay, and this ratio comes out to be what? Okay, so beta by k, which is nothing but dou p by dou t at constant v, this is nothing but this, which comes out to be 24 degree centigrade inverse. Okay, the option is A. Okay, degree centigrade inverse bar into degrees, because you see bar is -1, so it will go up. So it will be bar into degree centigrade inverse. Okay, so this will be the answer. Option A. Okay, so the explanation is clear to everyone. If no, then this is the right time to ask. Okay, and also one clue about how you can say that we have to consider here, like you said, the volume is constant. How do we consider it? You can see here. Okay, because it has considered volume constant, and we are to find dou p by dou t at constant v. There, hence we are considering volume as 0. Okay, hence we are considering this is 0. This is because of this becomes 0. Because of this becomes 0. Then we rearrange and then we find this dou p by dou t v is equal to this beta by k, and beta and k values are already given. Okay, so similar to this question, I am giving you one homework question, which is the same question, but instead it goes one step further. Okay, so what is or liquid toluene at 20 degree and 1 bar? So this is initial temperature, initial pressure, volume expansivity is same, which is 1.49 10 to the power minus 3 degree centigrade inverse, and isothermal compressibility K is 62 10 to the power minus 6 bar inverse. Also here also beta and K are constant. Now what they are asking is the pressure generated by heating liquid acetone at constant V. Okay, so here V is constant, here also V is constant from temperature this to final temperature. So once you know this, so this is equal to, so this is equal to beta by k, which is nothing but this value. Then what you basically have to do is you just have to integrate. So this is 24, and then you integrate from some p to some p. Okay, and then like for example this, like here we had no dou p by dou t. So here dou p by dou t, dou p by dou t is equals to 24, right? So what we find is initial temperature Ti is 20, and then Pi is also 1 bar. Now they are giving Tf, final temperature is 30 degrees centigrade, and what is the pressure at this? Okay, so you just integrate this. So you just, how do you do? dP is equals to 24 dt. You integrate this from pressure of 1 bar to final pressure Pf, and you integrate it. Its temperature, initial temperature is 20 degrees centigrade to 30 degrees centigrade. And when you put in the values, you'll get Pf as equal to, so I'm giving you answer as well, 241. Okay, so this is the homework question. So if anybody, so this you can discuss within the next class. Although I have already told the answer, since even though if you have any questions, we can discuss it in the next class. Okay. So you can sort of think like this question number 7 and above question number 6 are interrelated. Question number 7 is expanded further part of question 6. Okay. Anybody has any question understanding question 7? So I'll give 2 minutes. If you have any questions, you can ask. Otherwise, we'll move on to the next question, which is predominantly on heat exchange. Okay, so this is a very conceptual question. Okay, so let us try to understand what the question is. An inventor says that his new concept of an engine, okay, while working between temperature limits of 27 degrees centigrade and 320 degrees centigrade, rejects 45% of the heat absorbed from the source. Okay, his engine is then equivalent to which of the following engines? Whether it's a Carnot engine, or it's a diesel engine, or an Impossible engine, or an Ericsson engine. Okay. So let us try to understand. So what we have in here, engine. Okay, we have an engine and temperature limits are 27 and 127 degree. So in heat engine, what we have is, so let us first understand what is the concept of heat engine. Okay. So what we have is, this is the heat engine, and main purpose of heat engine is that we have to extract work. So we have here source, which is called as a source. Okay, from here we extract QH amount of heat from it. This is at the temperature TH, and this is a sink. Okay, this is at a temperature TL, and we dump QH QL amount of it, and then we take out the work. Okay, so it's based on second and third law that total amount of heat cannot. So this is the amount of heat. Okay, so this is the heat which is taken out from the source. Now we know that from second law that all the heat cannot be converted into work, right? So we should have some surroundings wherein we have to dump QL amount of heat. Some efficiency has to be there. Okay, we cannot have the second law of thermodynamics prohibits us from having QH equal to QL. We cannot have this. Okay, we should have QL has to be non-zero. QL cannot be equal to 0. Okay, so if you do heat balance here, what you get? QH is equals to W plus QL. Okay, that means W is equals to QH by, sorry, QH minus QL. Okay, so this is the basically the concept of heat engine. Okay, and when we have so what is the Carnot principle? So Carnot principle tells us that there exists an engine which is called as a reversible, which is based on which is called as a Carnot heat engine, which is based on the reversible uh, of cyclic process, which has the highest efficiency. There cannot be any engine operating between the same temperature range which has an efficiency greater than Carnot engine. Okay, and the efficiency of that Carnot heat engine is 1 minus TL by TH, which is nothing but 1 minus QL by QH. Okay, so when you give here TL and TH, so the temperature has to be in Kelvin. Okay, so let us try to understand what is the efficiency of the Carnot heat engine operating between 27 and 327 degrees centigrade. If that efficiency, let's say that efficiency is eta C. If that efficiency eta C is more than this 45 percentage, then we can say that this heat engine is possible. So the claim made by the inventor is correct. Otherwise, if this eta C is less than 45, then we know that there cannot be such an engine. Okay, so let us see, eta is equals to 1 minus, so we have to add 273 to convert degree centigrade to Kelvin, plus 27 divided by 273 plus 327. Okay, so this is 1 minus 300 by 600, or what is So this is what? 273 plus 327. Okay. This is 600. Okay. So this is 1 minus 1 by 2, which is 50%. Okay. Let me just close it. Okay. So remember what this question is that, okay, huh? So this question is that it is rejecting 45% of the heat is rejected, absorbed from the source, converted. Okay. So that means efficiency is 1 minus 0.45, right? It is 55%. 55%. The efficiency which the inventor is claiming is for 55%. Okay. So if you can see it from here. Okay. Okay. So the answer is impossible. So how why is that? So Carnot efficiency of this is 1 minus T2 by T1, which is TL by TH, which is nothing but 1 minus 273 by 227 plus 273 divided by 327 minus 273, which is nothing but 0.5. But according to the inventor's claim, the efficiency of engine is 1 minus 45 because 45% of the heat absorbed from the source is converted into work, right? That means efficiency is 1 minus of that, right? So it is 55%. So the Carnot heat efficiency is 0.5, whereas the efficiency of the cycle made by the inventor is 55. So clearly this is impossible. We cannot have an engine. This is the law of thermodynamics, right? So hence the efficiency of an actual heat engine cannot be greater than Carnot engine. This is an impossible engine, right? Hence the correct option is option C, an impossible heat engine. Okay. So I think the question is clear to everyone. So I'll give 1 minute if you have any questions. Right. Remember, do not confuse this with the efficiency. See, this is added to trick. This is eta is not 45, right? Eta claimed by for this 0.45. Eta is 1 minus 0.45. It is given in this indirect form to confuse the students. Okay, this 0.55. Okay, remember. So every time you solve a question, read question 2 times, 3 times, and read it very carefully. Okay, so I'll give 2 minutes. If anybody has any question, they can ask. Okay, so no questions. We'll move on to the next question. Okay, this is also based on Carnot cycle. Okay, so what we have here is an engine working on Carnot cycle rejects 40% of the absorbed heat from the source. Remember, okay. So keep in mind that this is similar. This is not the eta. This is not the what I can say, the efficiency of heat engine, but 40% of the absorbed heat from the source is rejected to the sink. Okay, while the sink temperature is maintained at 20 centigrade, then what is the source temperature? So let us first understand what is. Let us try to draw the schematics of the this question. So what we have is we have a source which is at a temperature TH. Let's say SH. SH denotes the source, and then there is a heat engine, reversible Carnot heat engine. It is extracting QH amount of heat from the source, and it is dumping QL amount of heat to the sink. Okay, so let SL become C, and it is at temperature TL, and the work extracted is W. Okay, so we know that efficiency eta is equals to 1 minus TL by TH, which is nothing but 1 minus QL by QH. Okay, that means TL by TH is nothing but QL by QH. And then one more expression which we have is QH is equals to QL plus W. Okay. So what it is saying that 40% of the adsorbed heat from the source is dumped. Okay, that means QL is 0.4 of QH. Okay, so when you put this expression into this, what we get is, and what we get is TL by TH is nothing but QL. QL by QH is what? This is 0.4 QH by QH. So this cancel out, and it is given that sink temperature is 27 degrees centigrade. That means TL has been given. Okay, so what we'll do is change the color, and I will be writing it here. So what we have is 27 plus 273 by TH is nothing but 0.4, right? This implies TH is 300 by 0.4. So majorly the mistake which is done is in this. You just take, instead of adding 273, you just take 27, which gives the wrong answer. Okay, so you have to convert it into Kelvin. Okay, so TH is equals to 3 into 100 by 4, which is nothing but, okay, okay, so it will be, let me just write it. So it was 300. Okay, I think I removed it. Okay, so this is equals to, okay, so this is equals to 0.4, right? This implies TH is equals to 300 by 0.4, which is nothing but 3 into 1000, right? And 200 into 30 into 100 by 4. So we just do it, which is 750 Kelvin. So when you convert it into degree centigrade, you get this. So minus 273. Okay, it will give you 477 degrees centigrade. The correct answer is option B. Okay. So now we'll look it in a formal way, typed format, in case you are not able to understand it. So let me first remove this. Okay. Okay. So this is the expression. Okay. Right. This is the schematics of the figure, that we have a source. This is source. This is sink. Its temperature is given as 27 degrees centigrade. When we convert it into Kelvin, it's 300. And QH amount of heat is extracted. 0.4 of Q is given. That means this is 0.6 of Q. Okay. So let us, okay. So the sink temperature is 300 Kelvin. It is given that the engine rejects 40% of the adsorbed heat from the source. Hence, and for Carnot engine, we have this expression. So one represents the source and Q2 represents the sink. So you just put it there, okay? Because 40% QL is 40% of QH. You just put in the values, you get 300 by 0.4, you get 750 Kelvin, which is nothing but 477 degrees centigrade. Okay? So is it clear to everyone? If anybody has any question, they can ask. I'll wait for 2 minutes. Is this clear to everyone? Okay. So I hear no question. So I assume everything is clear to everyone. And then we'll move on to the, so I'll give, so we'll move on to the next question. So what we have is question 10. So what is given? A heat engine having an efficiency of 70% is used to drive a refrigerator having a coefficient of performance of 5. Okay. So the energy absorbed from low temperature reservoir by the refrigerant for each kilojoule of energy from high temperature source by the engine is what? So these are the option: 0.14 kilojoule, 0.71 kilojoule, 0.35 kilojoule, and 0.71 kilojoule. So let us just, so this is the schematics. Okay, so this is an heat engine which is working between the temperature. This is the source, this is the sink. Temperature is TH, temperature is TL. Q1 amount of heat is taken out from the source of the heat engine, and Q2 amount of it is dumped into the sink, and some amount of work is extracted. So that work is nothing but Q1 minus Q2, and this work, like it is said here, is that is used to drive the refrigerator. Okay, so this amount of work is used to drive a refrigerator. So let us uh, you have, in order to do this, what you have to understand, what is an heat engine and what is a refrigerator. The heat engine is usually used to convert heat into work, whereas in refrigerator we do the opposite. In that, we do some amount of work to extract some amount of energy from uh, sink, from source, so that it is maintained at some temperature. Okay, so the amount of heat which is extracted from the heat engine, it is fed into the refrigerator, and this is maintained at some temperature T, and then, okay, so this is the schematics. So with this schematics and with this question, try to answer the question. So I'll give you 2 minutes so that you can figure it out. If you have any doubt, you can ask me, and I'll give you 2 minutes to try the question. Okay. So is the question clear to everyone? Okay. So was anybody able to answer it? Anybody able to solve it? The answer is 3.5 kilo. So nobody. So let us try to understand. So heat engine having an efficiency of 70 is used to drive a refrigerant. Okay, which has a coefficient of performance of 5. And what we are asking is the energy absorbed from the low temperature reservoir by the refrigerator for each kilojoule of energy from high temperature source by the engine. So what we are asked to do is, we are asked to find a ratio. Ratio of what? Q3 by Q1, which is Q3 by Q1. So how much amount of energy will be extracted from this per kg of per unit of energy extracted from the source of the heat engine. Okay, so what we are given is COP, coefficient of performance of refrigerator, has been given, and efficiency of the heat engine has been given 70%. Okay, so what we are going to assume? We are going to assume it's a Carnot heat engine. Okay, and by definition of COP of refrigerant, what we have is definition. It will be output by input, and for refrigerant, what will be the output? So we are in so output will be this, because it is we want to keep the temperature of this object at some temperature, and in order to achieve it, what we are doing is we are putting this much amount of work. Okay, so Q3 by Q5, Q3 by W, this is nothing but 5, and energy eta of heat engine is W by Q1. Here it will be also output by input. So here output is work and input is Q1. So it will be W by Q1. So if you want to remember, it is difficult for you to remember the formulas. What you can do is any efficiency is always going to be output by input. Okay. For heat engine, what we have is this is the input and this is the output. Hence, for heat engine, it's going to be, because this is what we are doing and this is what we are getting. So output is W by Q1, or you can say QH. Okay, and for refrigerant, what we need is we need to maintain temperature of this object at some temperature, let's say T3, and in order to achieve this, we are putting input. Okay, so for and efficiency or COP of refrigerant is nothing but output by input, which will be Q3 by, here it will be W. Okay, okay, so Q3 by W here and W by Q1 here. Okay, so this is the way which in which you can remember it. If it is difficult for you to remember the formula, you can derive it like this. Okay, so let us go back to the question at hand. So what we are given is this. We are given this, that COP is Q3 by W is equal to 5, and eta efficiency of heat engine is this. So what we want is we want Q3 by Q1 is what we want, right? The energy absorbed from low temperature reservoir. This is the low temperature reservoir, and this is the amount of energy absorbed by the refrigerator for each kilojoule of energy from high temperature of the source of the engine. High temperature, that is the source of the heat engine, is this. So what we want is Q3 by Q1. So if you are able to get from this, what we need is we just need to multiply this. Okay, there's a WW will get cancelled, and we get the Q3 by Q1. Hence these formulas or these definitions are very important. Okay, so what is Q3 by W, which is nothing but 5 multiplied by 0.7. It gives us Q3 by Q1, which is 7 pi as 35 and 1 decimal, so 3.5. Okay, hence the answer is this one. Okay, 3.5, right? So is 3.5, hence the energy absorbed Q3 from low temperature reservoir by the refrigerator for each kilojoule of energy from high temperature source by the engine is this one, 3.5. The ratio is 3.5. Okay, so anybody has any questions? So I'll wait for 2 minutes. If anybody has any question, they can ask. And those of you who are able to solve and do not have any question, they can try the next question. Okay, so I'll give 2 minutes. Okay, and then we'll start solving this next question. Meanwhile, if anybody has any questions on this, they can ask. Okay, no questions. So we'll move on to the next question, that is question 11. So remember, an irreversible heat engine. Okay, so the point which is to be noted here is it's an irreversible heat engine. Very, very important. It's an heat engine. Okay, very, very important. Extract heat from a high temperature source at the rate of 100 kilowatt. Okay, and rejects heat to a sink at the rate of 50 kilowatt. Okay, so this is what our QH has been given this, and this is QL has been given this. Okay, the entire work output of the heat engine is used to drive a reversible heat pump. Okay, so in the last question we had, the work extracted from the heat engine was used to drive refrigerant, uh, refrigerator, whereas here what we have is heat pump. Okay, operating between a set of independent isothermal heat reservoirs. So the heat pump is operating between these reservoirs. Okay, one reservoir is at 17 degree, other is 75 degrees. So what we are asked is the rate in kilowatt at which heat pumps delivers to its high temperature sink, right? So what we have is, so if we were to draw the schematics, let us try to. So this is the schematics which we have. Okay. So what we have an heat engine, and remember, this is an irreversible heat engine. It's not reversible heat engine. Okay. So this heat engine, irreversible heat engine, is operating between this source and this sink. It is extracting Q1 amount of heat, which is nothing but 100 kilojoule, which has been mentioned here, and 50 kilojoule is dumped to the sink. Okay. So Q1 is 100, Q2 is 50, and then the amount of work, okay, which you can easily find out, 100 is equals to W plus Q2. W comes out to be 50 kilowatt, and this work obtained from the heat engine, irreversible heat engine, is used to drive a heat pump, which operates on its independent sources, right? It's been mentioned here. Independent isothermal heat reservoirs at 17 degrees centigrade and 75 degrees centigrade. Okay, so this is the 75 degrees centigrade, which when converted into Kelvin is 348, and this is the other source, sink, other temperature reservoir, which is at 17 degrees centigrade, and when converted into Kelvin, it's 290 Kelvin. Okay, and what we are asked is the rate at which the heat pumps delivers to its temperature sink is. Okay, so in order to find it, so what basically we are asked to find is, we are asked to find what is the value of this Q3. It is given this Q1, Q2, W, and the temperatures T3, T4. What we are asked is Q4. Okay, so clearly, like I said in the previous question also, here also efficiency of heat pump will be what? Output by input, right? So what is the input? Input is the W, and output is, what is the output? Here the output will be now Q3, right? Here the output will be Q3 because in the previous question refrigerant. So in refrigeration, what we had, our goal was to maintain this at some temperature, but in heat pump, we want to maintain this temperature, right? That is why the name heat pump. Although the uh, process is same, but the target property is different. Target is different. In refrigeration, target was to maintain this temperature, and in heat pump, target is to maintain this temperature. That is why the output will be this. That means this is Q3. Okay, this is eta heat pump. So somehow, and we are asked to find this. So if somehow we are able, we already know what this W is, right? This is the W, and we are to find this. So clearly, if somehow we are able to find what is the efficiency of heat pump, we would be able to find Q3. We just have to multiply it by 50. Okay. So is this clear to everyone? Okay. So let us, if this is clear, let us go down and try to understand it. Okay. 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 Like I said, the coefficient of performance, if somehow we are able to find this, then we are done. Right. So the given coefficient of performance is output by input. This is Q3 by Q3 minus Q4. You can see here Q3 minus Q4, which is nothing but W, and W is nothing but 50. Right. For reversible process, we know. Remember, this is irreversible. However, this is reversible. Okay, the heat engine is irreversible, but the heat pump is reversible. Hence, we can use this expression, right? And hence, when we rearrange it, we substitute it Q3 by Q4, T3 by T4. What we get is coefficient of performance of heat pump is T3 by T3 minus T4, right? Which you can see from here, right? T3 by T4, which is nothing but Q3 by Q4, right? That we are just substituting Q3 by Q4 here to divide by Q4, Q4. So it will be like this. Okay. So now clearly we know what is T3, right? T3 is 348 Kelvin, T4 is 290 Kelvin. So we know the left hand side. On the right hand side, we know what is W. W is 50 Kelvin, kilowatt. So we can clearly find what is Q3, right? We just substitute the values, right? 348 by 348 minus 290, okay, is equal to Q3 by 50. And then we just multiply both the sides by 50, and we are able to get Q3 as 300 kilowatt. Okay. The correct answer is option C, right? So it is very important in such question that you draw the diagram, right? The systematic diagrammatic representation is very important, right? Like this. So always try to draw the diagrams. It will help you in understanding. Okay. So anybody has any questions? So I will give you 2 minutes, everybody. Okay, so I will give everybody 2 minutes to, if anybody has any questions, they can ask. And those who do not have any questions, they can go and try to solve the new questions. So I'll give you 2 minutes. Okay. If anybody has any questions, they can ask. Everything is clear to everyone? So let us go with the next question. Okay. So heat pumps, remember what we have? The heat pump is used to heat a house in a winter, and then reverse to cool. Okay. Reverse to cool the house, reverse to cool the house in summer. Okay. So the device is used as both heat pump and a refrigerator. Okay. In summer, it becomes refrigerator, or it works like an AC. It cools the house, and in winter, it heats the house. Okay. The inside temperature of the house is to be maintained at 20 degrees centigrade. So this is the set point. Irrespective of whether it's a summer or winter, we need this temperature, okay, inside the house. The heat transfer through the house wall is 7.9 kilojoule per second. Okay. So the house is not insulated. It is interacting with the surrounding as well. Okay. And the outside temperature in winter is 5 degrees centigrade. So what is the minimum power required to drive the heat pump? Okay. Okay. So first, so I'll give you 2 minutes to try. So remember to draw the schematics. Okay. So how does heat pump work? Like this. So we are doing some amount of work. Okay, this is heat pump. This is TH. This is TL. This is like this. This is like this. Okay. This is house. Okay. This is the surrounding. It's maintained at 5 degrees centigrade. We have to maintain this at 20 degrees centigrade. Okay. And then amount of heat lost. How is heat losing? So this is QH. This is QL. So one of them is 7.9. And we are asked to find W. Okay. What is the minimum power required? Okay. So with these hints, try to solve the question. Okay. I'll give you 2 minutes. So anybody has any question in understanding this question number 12? Any difficulty? They can ask. So anybody is able to answer the question? Okay. Okay. Let me draw the schematics. Okay. This is heat pump. This is TH. This is TL. This is like this. This is like this. QH. QL. This is our house. And this is surrounding. Okay. This is given to us as 20 degrees centigrade, which corresponds to 293 Kelvin, right? This is given as 5 degrees centigrade, which corresponds to how much? 279. Okay. And we are given this QL, right? So coefficient of heat pump is Q1 by W, right? This is Q1, this is W because it's a heat pump, right? So our aim is to do this. And like I said, eta is equals to output by input. So input will be W and output will be this one, right? QH or Q1. Q1 by W, and then W is nothing but we have W is equal to W plus QL is equals to QH, right? That means W is equals to QH minus QL, right? And when you convert this, assuming that the heat pump is reversible, you do this Q1 by Q1 minus Q2, which is nothing but eta becomes T1 by T1 minus T2, right? T1 is already given 293 Kelvin and T1 minus T2 is 293 minus 279, which corresponds to 50. Okay, W is this, right? 7.9 multiplied by this. So remember, this is Q1 by W, right? I think I have to. Okay. So remember this Q1 by W is T1 by T2, and what we are doing, we are evaluating this form, right? So T1 is 293, T1 minus T2 is 293 minus 273, which is 15 degrees centigrade. So when we simplify Q1 by W, it becomes 293 by 15. And what we need is we need to find W, right? But what is the minimum, right? So then we rearrange it, which gives us W is what? Which gives us W as Q1 into 15 by 293, right? And Q1 is what? This is given here, 7.9. So we just substitute it and then we get W as 415, 405 kilowatt, right? Because kilojoule per second is nothing but kilowatt, right? So correct answer is option B, right? 405 kilowatt. So anybody who has any question or this question or solution is not understood, who is having any difficulty, they can answer, they can ask. Okay. In the meantime, I will clear the screen. So is this clear to everyone? Right? I'll wait for 2 minutes. right? For those who do not have any question, they can go for the next question. And those who have any questions, they can ask. Okay, I'll give you 2 minutes. Okay, anybody has any questions? Otherwise, we'll go to the question number 13. So question number 13, heat in the amount of 100 kilojoule is transferred directly from hot reservoir, which is at 1200 Kelvin, to a cold reservoir at 600 Kelvin. So calculate the entropy change of the two reservoirs. Okay. So remember, the body who is at a higher temperature, its entropy is going to decrease, whereas entropy of a body at high temperature is going to increase. And what we are asked to find is, we are asked to find the sum of both the things, right? System plus surrounding, right? That is what we are asked. Okay. So what we basically have is, always try to draw the diagram. Okay. So what we have is, this is what we have. This is connected like this. This is at 1200 Kelvin. Okay. This is at 600 Kelvin. And hot reservoir. This is hot. Okay. And this is cold. And 100 kilojoule of energy has been transferred. And we are asked to find what is the entropy. So remember, entropy is what? Is Q reversible by T. Delta Q reversible. Delta is equal to delta Q reversible by T. Okay. So this will be what? Try to answer with this diagram. If anybody can answer, I'll give you 2 minutes to try the question. And the correct answer is this. Remember the unit as well. Okay. 2 minutes. So anybody has any difficulty in understanding the question, they can ask. Let us start. Nobody? Great. So I'm starting. Everybody check your answer. So this is the schematics. Okay, we have a body at 1200 degree Kelvin, and the other body is 600 Kelvin. The heat interaction between them is 100 kilojoule, and we are asked to find the total entropy change. So remember, entropy of this is going to decrease. Entropy of this system is going to increase. However, we are asked to find delta S1. Let's say entropy change of this is delta S1. Entropy change of this is delta S2. We are asked to find delta S total, which is nothing but sum of individual change in entropy. Delta S1 plus delta S2. And from the definition of entropy, we know delta S is nothing but delta Q reversible by T. Right? So this is, let's say this is H we denote, and this is L we denote. So delta S will be QH by TH. plus QL by TL. So remember, this is losing 100 kilojoule of energy, whereas this is gaining 100 kilojoule of energy. So QH is going to be minus 100 because because the body at 1200 Kelvin is losing energy. That's why QH is going to be minus 100, whereas QL is going to be plus 100, right? And the temperatures are 1200 and 600, right? So it is minus 100. Let me, right? So this is for this, right? And this is for this, right? So what you do, you just simplify this and then we get the answer as this, right? You just multiply this by 2, multiply this by 2, getting minus 100 plus 200 divided by 1200, which corresponds to 100 by 1200, which is nothing but 1 by 12, which corresponds to 0.0833. And the unit is kilojoule per Kelvin, right? Because it is mentioned Kelvin and here it is mentioned kilojoule. So kilojoule per Kelvin. Okay. The answer is option C, right? Anybody has any question? They can ask, right? Anybody who didn't understand it? I'll give you 2 minutes. Okay. The correct answer is option C, right? So those of you who were able to understand and have no questions, they can start with the next question, right? Question number 14. And those who have any questions, they can ask, right? And those who are still doing the question number 14, just do it fast. Okay. So nobody has any question. Then we'll move on to question number 14. Okay. The question goes like this. So consider two bodies of identical mass M and specific heat C used as thermal reservoirs. Okay. Which is source and sink for a heat engine. Okay. The first body is initially at an absolute temperature TA1. That means TH is T1, while the second one is at a lower absolute temperature T2. That means TL is T2. Heat is transferred from first body to the heat engine, which rejects the waste heat to the second body. This process continues until the final temperatures of the two bodies TF becomes TF, which is equal. And then which of the following is correct? Answer is option A. So I'll give you 2 minutes to think on the question and remember to draw first the diagram. Then it will become easier. Okay. This is quite an interesting question and is extension of question number 13. Right? In question number 13, what we had is just a food for thought is we assume this temperature to be same, not same, constant, right? But here the temperatures are not same. The temperatures are varying. Why is it? Because both the bodies have some finite specific heat capacity. Here we assume that the indirectly what we assume is the specific heat capacity of these both the bodies is infinite. That means no amount of heat, whatever amount of heat we take out from this body and whatever amount of heat which we add to this body, the temperature of these bodies do not change, right? So it's like an infinite heat bath, right? That is what we assume. Whereas here, the here what we will be having is we have a source, we have a heat engine in between, and this is the sink, right? This is H, this is L, this is TLH, this is TL, this is QH, this is W, this is QL. So what we are basically saying, as QH amount of heat is extracted from this, its temperature also decreases, right? TH to TH dash to again TH double dash. Its temperature is increasing. TL to TL dash to TL double dash, and this process will continue, and then a point will come in which the temperature of both the things becomes equal and no heat transfer is possible, right? And so we have to find that temperature. Okay. So I'll give you 2 minutes to try the question. So anybody able to find the answer? Okay, then I will start. Okay. So remember, the correct answer is option A, under root T1 T2. Okay, anybody got the answer? Okay, let us check. So what we have, this is the schematic, right? This is the schematic. This is the source. Okay, at temperature T1. This is the sink. QH amount of heat is extracted from the source, whose mass is m, specific heat capacity is C, and temperature is T1. It is fed to a heat engine. We'll assume that the heat engine is reversible. Then it is extracting some amount of work, and the rest of the energy is dumped to a sink whose mass is m, specific heat capacity is C, and temperature is T2, and the heat dumped is QL. Okay, we'll use the entropic relationship. Okay, so what we have is, okay, maximum power for maximum power protection, the entropy of generation must be zero. That means entropy of this full system must be zero, because the whole process should be a reversible process. We know that for reversible process, the entropy of generation should be zero. Okay, and it will be a very slow process, and it will have higher productivity, right? So taking the source, the sink, and the heat generation as our system. Okay, that means this full is our system, right? Full, all three combined together is our system. And entropy, so individually its entropy can increase and decrease. Individually entropy of heat engine can increase and decrease, and individually entropy of sink can increase and decrease, but the combined should be zero, right? That means the cumulative effect of all these three together should be zero. That is what entropy of generation is, nothing but entropy of source, entropy of engine, entropy of sink. It has to be equal to zero. And entropy of source is nothing but, we know that this, we know that ds, what is ds? ds is nothing but dq, or you can say delta q, reversible by t. And as the full process is reversible, this is also reversible. Individual cycles are also reversible. Individual processes are also reversible. I covered this in the first class, right? So if you integrate it, so q for this will be what? mcpdt, right? mcdt by dt, right? For source and sink, right? And anyways, as a cycle is a reversible cycle, heat engine is a reversible one, the total entropy changes for this is going to be zero, right? And when you integrate this for system, for source and sink, you get this expression, right? So initially the source is at temperature T1, finally it will be TF. The entropy of generation for engine is 0 because it's a reversible cycle, and as entropy being a state function, as the cycle comes back to its initial position, the entropy change is going to be 0, and for a sink it is TF by T2, right? So how did we get this formula? It is ds equal to mc dt by T. Right? So let me just clear it out, right? So TF is the final temperature. Okay, this is the expression, and this is equal to 0. That means this is 0. That means we have this. So we take mc mass of the mn to mnc common, and then we get the expression ln tf by t1 plus ln t2 by t1 equal to 0. This corresponds to what? We know log of a plus log of b is nothing but log of a into b. That means ln of tf square by t1 t2 equal to 0. That means tf square by t1 t2 is equal to 1. That means tf square is equal to t1 t2, which results into tf being equal to under root of t1 by t2, t1 into t2, right? So anybody has any question? So the correct answer is option A, right? Under root t1 t2, right? Anybody has any question? They can ask. Okay. So anybody has any questions regarding this question? Anybody who didn't understand anything, they can ask. We'll go to the next question, right? So those who don't have any question, they can start with this question number 15. Okay. I'll give you 2 minutes to try the question. Okay, so let us read the question. So what we have, a solid metallic block weighing 5 kg has an initial temperature of 500 degrees centigrade and 40 kg of water initially at 25 degrees centigrade is contained in an insulated tank. Okay, the metallic block is brought in contact with water. The specific heat of block material is this. Ignoring the effect of expansion, contraction, and heat capacity of tank, the total entropy change is very close to what? Okay. So what we have, let us always try to draw the schematic. So what we have is, we have an insulated tank. Okay, this is insulated and it is filled with water. Okay. Now what we have, its temperature is, initial temperature is 25 degrees centigrade and its initial mass is 40 kg, right? Now what we have is, there is a block also, metallic block of 5 kg and initially at temperature of 500 degrees centigrade. So this we brought in this contact. Because of this, what will happen is, temperature of the block will decrease and temperature of the water will increase, right? That means entropy of this block will decrease and entropy of the water will increase, right? And what they are asking us is, ignoring the effect of an expansion and contraction and the heat capacity of the total entropy change. That means entropy change for this block plus entropy change of this water is what? So remember, this all we are considering as one system. So even if you do not know, you don't do any calculations, just by logic, you can remove one of this, one of the logic, one of the options, right? Because this when we say, it becomes an isolated system, right? And entropy of this system should always increase. Individually, entropy of this 5 kg block can increase and decrease. Individually, the entropy of water can increase and decrease, but the combined effect should be increase. That is what is the third law. That is what is the second law tells us. And that means this cannot be an option, right? Delta S has to be either 0 for reversible process or it has to be positive. So clearly, this is not an option, right? So try to find. Okay. So this will relate very nicely to the previous question which we had, in which what we did is ds equal to mcp dt by t, right? So you can use that formula to find the entropy change. So I'll give you 2 minutes to try it. The correct answer is option C, 1.28, 1.26, right? Anybody able to get it? I'll give you 2 minutes. Okay, anybody got it? We will start. Okay. So like I said, that temperature of the block will decrease and the temperature of the water will increase, and it will come to an equilibrium state, right? So let's say that final equilibrium state is temperature is Tf, right? So entropy, so energy lost by block is nothing but energy gained by block, right? Because it's an insulated system, right? Let me just, right? Entropy lost by block is equal to, energy lost by block is equal to energy gained, and energy is nothing but mcp dt, right? Energy lost by block is mcp dt of block, which is equals to mcp dt of water. So mass of block is 5 kg, its Cp is 0.4, and initial temperature is 500, and final is Tf, right? So m Cp dt block is equal to mass of water is 40 kg, initial temperature is 25, and here Tf, right? Using this, we find the final temperature, which corresponds to around 303 Kelvin, and then total entropy change is nothing but entropy change of individual system, which is nothing but mcp dt of block plus mcp dt of water. Mass of block is given as 5 kg. CPO is already given. TF now we have just calculated. TI we know 500 degrees Celsius. Remember to convert degree to Kelvin, right? Degree to Kelvin. Right? Similar is the case with water. We know that M here is 40, CP is 4.18, TF is this, and TI is 25 degrees. So just which is 298 Kelvin. We just put it, and then we find this positive. So remember, this will be a negative quantity. However, this will be a positive quantity, and the sum of these two things has to be positive as per the second law, which it is, which is a this you can use at a cross checking at 1.249 kilojoule per kg per Kelvin, which corresponds to 1.26. Very close to, right? So the correct answer is option C, right? 1.26. Anybody has any doubt in this question? Otherwise, we will move forward. Okay, nobody has any question. So those who are writing, who are done with this can go with the next question, and those who want to ask any question they can ask, right? So nobody has any question. Nobody has any questions, then we'll move on to the next question, right? Which is question number 16. So what we have is a unit mass of a substance undergoes an irreversible process. Remember, it's an irreversible process from state 1 to state 2 while gaining heat from the surrounding at temperature T. Surrounding temperature is T in the amount of Q. So heat is gained. Surrounding is losing temperature, surrounding is losing the heat, and the system is gaining heat, right? And the quantity of heat exchange is Q. If the entropy of the substance is S1 at state in 1, that is initially, and S2 at final state, the entropy change of the substance delta S during the process is what? So remember that the process is irreversible. However, the entropy is a state function, right? It does not depend on the path, whether it's a reversible or irreversible. Entropy is always defined for the reversible path connecting 2 points, right? So using this, you try to answer it. Right? It's a conceptual question. Right? I'll give you 2 minutes. So anybody got the correct answer is option C, right? Anybody got it? Okay. So this is a conceptual question. Remember, even though the process is irreversible, there is no such thing as called as a entropy change for an irreversible process. The process can be reversible, but the entropy is defined only for a reversible path. It does not. It doesn't depend on path. It's always for the reversible path, right? So even though the process is irreversible, the delta S is going to be the same, which is S2 minus S1, since it is independent of the path, right? Entropy is a state function, hence is independent of the path, reversible or irreversible of the system. Hence the option is option C. Correct answer is option C. Okay. Anybody has any question? Anybody? Everyone understood it? If you have any questions, you can ask. Those who have understood it can try to answer this question, right? So this is straight away from the lecture, right? If you have read the lecture, or if you have listened to the lecture, you will be able to answer this question, right? Option says this, right? You have to match the pairs that and the left hand. So what is the question? Match list one, which is a stability criteria. So these 4 are the stability criteria with list 2, which is an originating equation. So CV greater than 0 will originate from one of these reason. Okay, and select the correct answer using the code given below. Okay, so this is the stability criteria, and let's say for example this is the stability criteria, and when you simplify this expression, you will get one of these 4. Similarly, this is the stability criteria, and when you simplify it, you will get one of these expressions. Okay, these are the options. So this is straight away from the lecture. So I'll give you 2 minutes. Okay, so correct answer is option A, right? A4, A4, B1, C3, D2, right? So what is the answer? So upon simplifying the entries of list 2, right? When you simplify this expression, you will get this. Okay, we get the entries of list 1, and you have if you want to find as the simplification is a tedious and very lengthy process, I'll refer to the lecture 27 of the course videos. Right? If you go to the lecture 27, you will be able to find the full explanation for this, right? So we'll go to the question number 18, which is, so this is the first law, the basic expression for a closed system, right? And what we are asked is that consider du is equal to TdS minus PdV. The transformation to eliminate S by T in the above expression is called as. So it's a Legendre transform, right? So Laplace, it is not Laplace transform because Laplace transform comes in control theory, right? Fourier transform, it's a mathematical transform. It's a Legendre transform, right? So the next question which follows this will be that if you do this Legendre transform of S by T, right? So what expression you will get, right? In question 9, the Legendre transform will give us which of the following thermodynamic potential. Okay, so anybody would like to try? The answer will be this, right? So if anybody would like to try, you can try, and after 2 minutes I will give the solution, right? Okay, so what we have is du is equals to, so first let me write like this, u as a function of S and V, right? Du is equals to dou u to S at V ts plus dv, sorry, this is dv, and dou S dou V, sorry, dou u to V at counter entropy ds, right? Which is nothing but du is equal to minus PdV plus TdS, right? Okay. So let us first try to understand what is Legendre transform. Let us revisit and then I think we will be able to solve this. The correct answer is, I will give you the correct answer first. The correct answer is this one, option C, right? Legendre, Helmholtz free energy. Okay. This is the correct answer. Okay. So first let us try to understand what is Legendre transform and then we'll. So let's say we have a graph of y, which is a dependent variable, and this is x, and the values of the function are like this. And the relation between y and x is y is equal to f of x. Okay. So this is one way of plotting. So this is one way of correlating y and x, right? So if we somehow, if we are able to know f, we will be able to find y for the known values of x. So this is one of the way. So what? Okay. So another way of doing the same thing, okay, without any loss in the information is the other way. That means if you, what you do, you take each and every point, you take the slope of it, each and every point, and then we will be able to reconstruct the graph. So the information loss, either we do y is equal to f of x, or we take the help of the slope of the curve at each and every point, and then using that we will be able to construct a relationship between y and x. So this method is called as a Legendre transform, right? So Legendre transform will be of the form y is equal to mx plus c, because m will be the slope and c will be the intercept, right? So we'll compute the tangent, and let's say that phi, let's say, and that the new function which we develop is phi of x, which is equal to nothing but f of x minus summation of let's consider it's only a 2D two-dimensional representation. In that case, it will be del f by del x. Okay, so this will be the representation. So this expression and this expression both imply the same thing, right? They are just doing the or looking at the same thing from different perspective. This also has complete information. This also has complete information. Here we are using, we know the functional form, whereas here what we do is we take the derivative at each and every point. Okay, so this is what is Legendre transform. Okay, so now let us try to understand. Okay, So we'll go. Okay. So we have du is equals to TDS minus PDB. And what we need to do is we need to eliminate this S. So how will we go is we consider this is nothing but U is equals to U of S and V, and we need to find a function phi which will represent S. So we do not know what that will be. Let's say that will be X and the other will be V. Okay. So how do we do it? So when you compare it, what we have is, so when we so from this expression what we have is do U do S at V is T and do U do T at do U do U do V at S is minus P, right? Then we know that the new function will be phi of X, phi which is nothing but F of X minus dou F of X by dou X, right? So here it will be what? U, which is a function of P and V minus this. So here X will be, as we want to substitute X, so here will be X will be S, right? This is nothing but, this is into dx, right? So this is nothing but, sorry, this will not be dx, this will be dy, right? This is nothing but T into S. This is U minus TS, right? So what is this function? It's nothing but Helmholtz free energy, right? So that's how we get Helmholtz free energy, right? Anybody has any question in this? Any doubt? Right? So if nobody has any question, I'll assume that everything is clear. So as we have passed our allotted time, I would like to thank each and every one of you who have joined this lecture, and I hope that this initiative and these lectures which I am teaching will be able to help you. Okay. So I will ask if anybody has any questions. So if no, then remember to do this homework question, right, which is similar to the question number 6, and we can discuss if anybody has any questions on this. We can discuss this question in the next class, but do remember to do this homework question, and I hope that you are enjoying these classes, and I hope to see you again, okay, in the next class, right? So if nobody has any question, I think we'll stop right here. Okay, then we'll meet. We will meet next week. Okay. So thank you all for joining. Okay. I hope to see you in the next class. Thank you.